I'm Alex Walker, one of the engineers at Vaticle that built TypeDB. My talk to you today is about building a TypeDB client. What we'll do, we'll go through the code base of client Java and look at its overall architecture. The goal is that anyone watching will better understand how the clients work and how to build their own. First off, let's get an overview of our current clients. There are 3 official Vaticle client drivers: Java, Python, and NodeJS. And then there's the community client drivers. We have TypeDB Client.jl by Humans of Julia, Client Go by Tali Sins, in development clients in C#, Ruby, Rust. The only question is, what's next? So let's move on to the overall structure of an application using TypeDB. Let's say you have a database server and you want to query it in your application. To interface with it, you're going to need a TypeDB client driver which communicates to the server over Grpc. But just what is Grpc? Grpc is a modern, high-performance, open-source, universal RPC framework. Architecturally, it is an alternative to using simple HTTP calls for client-server communications. You can learn more about Grpc on their website, grpc.io. So, why does TypeDB use Grpc for messaging? Well, why not, let's say, use a REST web API? The simple reason is performance matters. And I've posted a link to an excellent blog post which compares Grpc to REST. It describes how REST actually outperforms Grpc for very, very simple calls. But where Grpc wins is in its ability to scale. Because instead of connecting to the server on each request, Grpc establishes a long-lasting connection which enables subsequent calls to be made faster. The payloads are encoded efficiently using the protocol buffers format. Now, neither of these things are novel concepts. We could use WebSockets for a long-lasting connection, we could use gzip compression, but why would we do that when Grpc can do it all for us, so we never have to think about any of that? Second point is the developer experience. Strong typing, as you might have guessed, is a big thing for us. On the right, I've supplied an example, how we encode an attribute value in protocol buffers. TypeDB has 5 different types of attributes: string, boolean, long, and so on. And each of them have their own strong types in our protocol. Another nice thing is, and this is particularly useful for debugging, given any client call, you can pretty easily find the matching code on the server. Here's an example. In client Java, in the method getInstancesRec, we here have code completion offering us all of the protocol field names to pick from. We have role type getPlayersRec, thing type getInstancesRec, thing type getOwnsRec. The one we're using for this particular method is called thing type getInstancesRec. And if we now search up the TypeDB codebase for that method, it comes up in a Java class called TypeService, the service that handles concept API methods. So yeah, this ability to trace code back to the server is pretty useful for debugging. Right, let's get on to the package structure of client Java. We've opted for a hierarchical structure without circular dependencies. This becomes really important in languages that can't resolve circular package references, such as Python. The root package labeled client Java at the top That just contains the entry point typedb.core client, the first thing that anyone uses when using TypeDB in their application. In the bottom left, we have API. API contains all of the interfaces for the code base. We named it API because those interfaces effectively define everything that a client can do. In the middle, core is where the basic building blocks are implemented. Client, session, transaction. Most TypeDB operations only occur within a transaction. So we've split their implementations up into the three packages that sit below core: query, concept, and logic. When building a client, a good place to start is always trying to make a single, simple RPC call. So let's begin at the core package. The entry point of a TypeDB client, as mentioned earlier, typedb.core client. The important lines to look at in this implementation are where we create the Grpc channel and the service stub. And what do these do? They set up a long-lasting server connection that we can execute methods on. It's worth noting, each implementation of Grpc does this a little bit differently. So to find out how it works in your language, you should consult the Grpc docs, because it won't be the same as in Java. So, we've made a connection. Now we should make some RPC calls over it. Let's build a TypeDB Database Manager. Database Manager provides 4 methods, which are used for creating and retrieving databases. These, and all the other RPC calls, are defined in the TypeDB protocol. So, remember the TypeDB core blocking stub that we saw just earlier in the Java code? That refers specifically to this service TypeDB core in protocol. That means it contains the database's create method and all the other service methods. So if you put that method into your code, then that's it. We now have a method to create a database. And if you try running it against a TypeDB server, then you should be able to find that you successfully can create a database on the remote server, thus completing your first Grpc call. Later on, we'll do more exciting things like TypeQL queries. So, to begin performing actual database operations, such as defining schema or inserting data, we need a session and a transaction open of the appropriate types. To give an example, you're not allowed to define schema inside a data session. A session is essentially a long-lasting tunnel from client to database. However, we are able to implement that tunnel with only basic RPC calls. Open and close are both simple calls. Now, sessions do consume resources on the server, and they can hold locks. If a client disconnects suddenly, say by crashing, the server needs a way to know. So sessions use a pulse mechanism. Every 5 seconds, a TypeDB client session should send a session pulse, which informs the server that the client is still alive. If the server doesn't receive any pulse in 10 seconds, then the server will time out the session, freeing up its resources for use elsewhere. Once the session's open, we can open a transaction inside it. A transaction is responsible for reading and writing to a database. This introduces a new kind of RPC call, a bidirectional streaming RPC. This is the thing that's comparable to a WebSocket, a long-lasting tunnel that allows the client and server to talk freely to each other, sending messages to each other, much like you'd use in a web chat app, for example. Something to note is, concurrently, a client can have many sessions. Session can have many transactions. Transaction can perform many queries. And all client implementations should support this parallelism. So, we've opened a bidirectional transaction stream. Let's look at what goes on inside it. The first message is always open.rec. This can be found in the transaction proto file in protocol. By convention, we call all of our requests rec and all of our responses res. For each rec, the server responds with a matching res. In this case, we get open.res, which simply confirms the transaction was opened. After that, we can send any other kind of message. So we have the Grackle define query. Sorry, the TypeQL define query. We have the request to create an instance of a type, which is concept API. The request to get a thing by its IID, and the request to commit. And these are just a few examples. On commit, the server will close the transaction, which ends the stream. Now, this model of bouncing requests and responses to each other synchronously works, but it does have a pretty significant drawback. Suppose the server is located in a different continent, or just for whatever reason you have high network latency. Then, each request-response pair is going to involve a network round trip, meaning even a few operations could take a very long time. In order to mitigate that, we support an asynchronous request-response model. So in this case, after the initial open request, we send define, type create, get thing, commit, all in one go. And we don't wait for the server to respond. The server is guaranteed to process those requests in the order they are sent. So it does so, commits, closes, ends the stream, and it does all that while significantly cutting down the number of network round trips, which massively improves performance for users with high network latency. So what we saw there was a sequence of single requests and responses. We can also do streamed responses. And the main use case for this is a TypeQL match query. Because match queries can return millions of responses, if not even more, we do not want to send all of those in one message. So we stream them. We split them up into these response parts. And each response part may contain a certain number of answers. So the first match res part could contain 20 answers, the second res part could contain 25, and so on. Now, there's no guarantee that the client actually needs all those answers. Suppose the client's request is to just do this query, iterate over the answers, but stop when we get to an answer that matches a given predicate. So, to avoid wasting server resources, we only auto-stream up to a certain limit, called the prefetch size. Then, the server sends a special message called continue. Continue indicates to the client that if it needs more answers, it should respond with a stream request. And that stream request should be passed with a request ID that matches the ID of the match request. Doing so indicates that the server should continue streaming, and when there are no answers left, it sends a done message. The client now has all the answers it needs, it's done with the query, so it closes the transaction ending the stream from the client side. I've attached a snippet from Client Java's response part iterator, which is responsible for processing these special stream.resPart messages, done and continue. Now let's talk about how the responses are collected. Whenever a request is made, we create a response collector, essentially a bucket that holds responses for the query. The bucket gets populated as answers are received from the server. The bucket gets drained as the user iterates over those answers. And this architecture enables concurrent requests. In this diagram, query 2 returns answers before query 1, but we ensure that they are all piped into the correct buckets. Now, Grpc does have some limitations. We discovered during benchmarking that message delivery actually became a performance bottleneck, because Grpc is only capable of sending so many messages in a given time frame. An easy way to look at this is taking a real-world example. Suppose you have a bridge, and you want to transport many people across it. It's not very efficient to pack those people into individual cars, but it is more efficient if they're in big buses. And that is what request batching does for us. In Client Java, request batching is delivered by a class named requestTransmitter. It collects all requests in a 1 millisecond time window, bundles them into a single Grpc message, and dispatches that bundle to the server. Right, I think we've talked enough about how messages are delivered. Let's talk about what they actually contain. The payload of a transaction message typically consists of TypeQL queries and/or concept API methods. Running queries is one of the most critical functionalities of a TypeDB client. Let's see what a query protocol message looks like. So the transaction.client message contains multiple recs, which can be of any request type. Note that transaction.client is the base message that you send in a transaction, if you're the client. The request types are openRec, which we saw earlier, commitRec for commit, rollbackRec to rollback, and so on. The one we're currently interested in is query manager rec. Every type of TypeQL query is covered in this message type: define, undefined, match. Each rec contains a single field, which is the query string. The only thing that actually differentiates these query types is their return types. Define doesn't return anything interesting. As you can see, its res message is completely blank in protocol. All it is a confirmation that the query actually ran. Match is more interesting. It returns a batch of concept maps, i.e. the query answers. Now, this is only a partial response. You see its name is resPart. And the full match response is made up of many resParts. Here's the full list of query types available in our docs and their respective answer types. All of them return awaitable or iterable objects. They don't block the main thread when the query runs. QueryFuture is a simple awaitable class defined in all TypeDB clients. If the user wants to block and wait for the query to finish running, they call its get method. But if they don't call that, then it simply runs asynchronously in the background. Then there's the stream and iterator methods. In Java, streams are an inbuilt thing. In Python, we use an iterator, and in NodeJS, we use an async iterator. Basically, just use whatever data structure is most natural in your client's language. Okay, let's look at the answers we get back from match queries. Match query returns a concept map. A concept map is a map of variable names to concepts. Concept is either a thing, instance, or a type. And each of these also have their own type hierarchies, as you can see in the diagram. Client Java uses a separate class to represent each of these different kinds of concepts. And each one has their own set of methods that we can use to perform various operations, either updating the concept or finding out more about it. One important use case of the concept API is TypeDB's visualizer, Workbase. In Workbase, when you double-click on a concept node, it loads all of its linked relations. In this example, we can see a large network of connected concepts. Right, I'll quickly give some notes on implementing the concept API. The client implementation of concept API is not exciting at all, but it does have a lot of methods. As an example, I've attached the getInstances method on thing type. GetInstances is available to all the subclasses of thing type, so that's entity type, attribute type, and relation type. Concept methods either return single or streamed responses. GetInstances is an example of a streamed concept method. Now, all concepts need to be identified so that the server knows what you're talking about. For things, we use the internal ID, and for types, we use the label. When it comes to testing, we do recommend using our behavior spec, which contains extensive tests for all features. It's written in a test syntax named Gherkin. Tests consist of a number of named steps. To run the tests in a new client, you need to implement those steps. While that might seem cumbersome, it saves a lot of time on the long run because it saves the need to write your own tests. You'll be testing directly from the TypeDB spec. Right, so that's all of the bits and pieces of a TypeDB core client covered. What about TypeDB cluster? Cluster is a distributed database system designed for high availability. In a nutshell, cluster features 3 or 5 or more individual servers which communicate internally to form a consensus when querying. Now, a cluster client deliberately has the same interface as a core client, but under the hood, they work differently. A cluster client constructs one core client per cluster node. In cluster, the system can tolerate failures and continue normal operation even in the event of a server outage. So what happens when we're opening a transaction to, say, node 1, and it experiences an outage? Well, the cluster client immediately reroutes the request to a different core client, which is then able to successfully communicate with its node. The client recovers from the failure and continues running as if nothing happened. And that concludes the section on building a TypeDB client. You now have all the knowledge you need to build your very own one. There is one more thing worth talking about, which is network performance optimization. The strategies employed by the TypeDB server to optimize performance. We've already looked at one, which is asynchronous request processing. Now we'll revisit that with a simple example. We're going to make 2 calls with the following conditions. Network latency of 100 milliseconds, so that's 50 milliseconds up, 50 milliseconds down. Let's say the client takes 10 milliseconds to construct a call, and the server takes 20 milliseconds to process a call. Assume no concurrency. Here's how the flow would go. Client takes 10 milliseconds to construct request 1, and another 50 to send it over the network. So at 60 milliseconds, the server receives request 1. It takes 20 milliseconds to process it, and 50 more milliseconds to send it over the network. So the client receives the response in 130 milliseconds. And that process then repeats for request 2, meaning the whole operation takes 260 milliseconds to run. With an async model, we can do much better. The first request still takes 10 milliseconds to construct. But then, while sending it over the network, the client can create and send request 2. The server receives request 1 at 60 milliseconds and request 2 at 70. But at 70, it's still busy processing request 1, so it only starts processing request 2 at 80 milliseconds. It's done with that by 100, and then takes another 50 to send it over the network for a total runtime of 150 milliseconds, significantly faster than the sync model. Okay, now let's look specifically at streamed responses. So a concept we briefly touched on earlier was the prefetch size. Suppose we're streaming 10,000 answers. For simplicity's sake, let's say each message contains just one answer. The default prefetch size that TypeDB uses is 50. So for every 50 answers, we also send a continue message. That gives a total of 10,200 messages sent by the server. But up to 49 of those messages may be simply discarded if the user doesn't iterate over them. You know, if it's done after the first item in the prefetch, then it throws away the other 49, then that gives us redundancy of 49. What if the prefetch size was 1? Then we won't have any redundancy. But we are also now sending an enormous amount of messages. 20,000 messages, and that's not even including the messages sent by the client. At the other end of the spectrum, what if we turn the prefetch size all the way up to 10,000? That would minimize the number of messages sent. We'd be down to just 10,001. But if the client doesn't need that many messages, then we're going to get a hell of a lot of wastage. In the worst case, the client could be done after just one message, leaving 9,999 redundant messages. Right. Now let's look into the timing of an answer stream. 50 answers, 100 milliseconds network latency, prefetch size of 10, 5 milliseconds time to compute an answer on the server. Here's how it goes. At 0 milliseconds, client sends the query. Takes 50 milliseconds to reach the server. From 50 to 100 milliseconds, the server computes and sends 10 answers and continue. Now, because of latency, the client gets those messages from 100 to 150 milliseconds. At 150, it sees continue and responds with stream to fetch more. The server sees stream at 200 and computes answers 11 to 20. This process then repeats until the server sends done at 700, which the client sees 50 milliseconds later for a total time of 750. As you can see, there are large gaps where work isn't being done. Ideally, we want the server to not have those gaps. There's an easy solution. Use a much higher prefetch size. That would take away the gaps. But we don't want to do that. As we mentioned previously, a high prefetch will lead to higher network load, higher server load, loads of redundant work. Like, even if the user knows that they actually need all the answers, their code might crash or throw an error. So we'd end up with wasted resources either way. How can we minimize the problem while also ensuring the user gets the best performance? What if instead of stopping at the end of a prefetch, the server keeps going for just long enough to cover that gap? The size of that gap is the user's network latency, so we measure it and compensate for it. Let's look at the effect. The server starts computing answers at 50 milliseconds, as before. But then, even before the client receives continue, the server keeps on working. In 100 milliseconds of latency compensation, it computes answers 11 to 30. At 200 milliseconds, it receives the stream request, which tells it to keep going. Compensation kicks in again at 250, and it sends answer 50 and done at 300 milliseconds, leading to a total runtime of 350. Essentially, what we've created is a predictive system. The server has guessed that the client would request more answers, and it ensured that they arrived even before it knew they were requested. And that concludes the talk. We now know the ins and outs of the TypeDB client-server architecture and how to build our own client. Thank you very much for watching. Do join us over on Discord if you haven't already. I've attached a QR code that you can scan on your device, which will get you into our server. And just before I forget, some of you may have already seen Mark's talk about the Julia client already. And I want to quickly use this opportunity to shout out to him and the Humans of Julia community. They've been a pleasure to work with on producing the Julia client. And partially, that's what inspired me to make this presentation. So thank you, Mark and Humans of Julia.